I'm just the behind the scenes host. I'm going to hand it over to your actual host, Dr. Doug Reichen.
Hi, everybody. I'm going to quickly pass it right along the line here. I want you to meet our amazing director, Dr. Sherry Wells is the director of AFOSR. And also on the weekends, she moonlights as Captain Kirk's replacement for the Starship Enterprise. Dr. Welsh, it's all yours.
Oh, thank you so much. I really appreciate it. Doug, were you going to introduce everyone, or you want me to go ahead and do opening remarks here?
The idea is you and then Pat, our chief scientist, will have opening remarks, and then I will introduce all my wonderful thinkers. Notice I said thinkers, not speakers, thinkers.
Thinkers, yeah. Got it.
Okay.
So good morning, good afternoon, good evening from wherever you're dialing in from. I do realize my camera's in an odd place. It's on the side of my computer. So I'm gonna look here so I can see people. So as Dr. Reichen said, I'm Sherry Welsh. I'm the director for the Air Force Research Labs, Air Force Office of Scientific Research. That's a mouthful. And at AFOSR, where Doug Reichen is thankfully one of our program officers, our job here is to discover, shape, and champion bold, high-risk, high-reward basic research for the Department of the Air Force. So that includes the Air Force and the Space Force. So we stay in that nice, crazy pocket of high-risk, high-reward research, which is a lot of fun for us. So some of the boldest research in our portfolio is in the science of information, computation, learning, and fusion, all of which contributes to the future of artificial intelligence capabilities for our national defense. So I'm thrilled to be here and welcome you. I think we had over 1,000 people register for this event, so we're really excited about that, and real happy to kick off this conversation with distinguished leaders or thinkers, as well as Doug mentioned, or as I like to usually call them, just our rock stars in the field of AI, right? This panel consists of an impressive group that represents partners from academia, industry, and the Air Force Research Lab. So a big thank you to our own Doug, Dr. Doug Reichen, for arranging this wonderful event and generating so much excitement around funding the next big question in AI. So to help frame why this topic is so important, the DoD is rapidly accelerating, as I think most people have heard, rapidly accelerating the adoption of AI to preserve its competitive military advantage and to build a fit force for our time. So like electricity or computers, we expect AI capabilities to be useful across the broad spectrum of DoD activities. So thoughtful, responsible, ethical, and human-centric adoption of AI really has the potential for us to positively transform all aspects of DoD operations, which is why this event is so important. So likewise, the Department of the Air Force knows that we do have to accelerate change to prepare for that future. It's imperative. We have to. We're at a real tipping point, I believe. So these kind of conversations are really crucial for us all to have across all of our communities. It includes the steps we take now in our investments and workforce experience to transition from the force we have today to the force that's required to meet the pacing challenge presented by China and our adversaries. So our partners in the American technology industry, defense industrial base, and academic sector all play that critical role. So we need your support. So I'm glad you're here. We need your support to effectively accelerate AI adoption for the Department of the Air Force and the DoD, because we can't do it alone, right? We need all those communities to come together. So an example of that support can be seen here today by the panel's willingness to engage in a very robust and ongoing dialogue. This won't be this is not going to be a one and done. So that ongoing dialogue that explores the science-driven questions and helps guide an AI future for the DoD that reflects our nation's values and gives the capability that we need. We all know that basic research is a long game. It's a high-risk pursuit of an idea, a challenge, or an unanswered scientific question that can often take decades to solve, right? So thank you all for being here, for pursuing those ideas and unanswered questions, for having this conversation, and inviting the entire S&T ecosystem to join you. So really appreciate all your planning to get here today, your perseverance and expertise and unwavering dedication that will end up changing the future for us. So with that, I believe this event, and if you know Dr. Doug Reichen, you know that this is going to be an amazing event. I've been looking forward to this for several weeks. So because of this event, I believe our lives are going to change forever and never be the same after this event. So these next big questions you're going to discuss today will keep the engines of innovation humming. This sounds kind of dorky, but it really is true. And so to emphasize the point of this changing our lives forever, I would like to quote Star Trek's Captain Picard when he was taken over by the Borg and he was Locutus. I think we have an audio clip, correct? To reflect our lives being changed forever here. Can we cue that up, Molly?
Dr. Welsh, can you just go ahead and say it? I was gonna kick it to Shelby, but it's better coming from you.
Oh yeah, I'm sorry. Your lives as it has been is over, as you have known is over. So meaning your lives will change forever after this wonderful conversation today. We might be having audio trouble. So if we are, I apologize. It's a cool clip. It's a cool audio clip. I thought it'd be a fun way to go ahead and throw it back over to Doug, but we might be having some problems. So with that, Dr. Reichen, I hand it back over to you, sir.
Oh, just plain old Doug. And I'll explain that in a second. I'm going to introduce our chief scientist at AFOSR. We've been friends for a long time. He is so impressive in his breadth and depth of science. He also, like our director, has an alias job on the weekends. He takes on the role as the chief scientist officer of the Starship Enterprise, covering for Mr. Spock. But Pat Roach is the chief science officer. He and I engage in conversations that we have to kidnap Jan LeCun to get involved in that deal with glia cells, not just neurons, glia cells and other biological elements that will be part of AI in the future. It's not just silicon, it's biology. It's not just biology, it's many things. I get carried away with it. I love this, but Pat is the real deal. Pat, all yours. Dr. Roach.
Hi, all. Pat Roach, as Doug said, I don't have the pointy ears, so I feel a little bit underdressed. I work for an incredible director with great insight and energy and foresight, who's brought new things to the Air Force Office of Scientific Research. And one of those is a pivot towards space and understanding that to get to that place, artificial intelligence, machine learning, trust and influence, all of those things combined together, right, are what we need for the future. I did not script my comments this afternoon because Doug asked me not to. Doug and I would spend hours and hours after he came to us from Columbia University discussing what was meant by artificial intelligence, going over and over the tenets of Marv Minsky, discussing that when you learn it once, you must continually learn it. I've been with both Cap and Tom Mitchell at MIT and the discussions that were had there, and those were really great, from what is practical to what is impractical. So I think I want to talk for a moment about what I see as the overpromise today of artificial intelligence, and looking at the distinguished group in front of me, maybe asking the question, what do you think is realistic? Managing expectations, I think, is critical in science and engineering. And if we do manage expectations properly, we can achieve great end that we so desperately need, that Dr. Welsh talked about. And we are at a pivotal moment. around the world in terms of the things that we need in terms of data information, accuracy, as well as the ability to have machines look at that data, cull through it very carefully, and do the kinds of things that we do as human beings, which is the bio-inspired part of what we want in terms of artificial intelligence. And Doug and I would talk for hours about how do we just put into a system, how mammals actually communicate with themselves and understand how is intelligence, human intelligence, right? How do we put that into machine type taskings and make that more like what we really want, which is ourselves, right? What are the fundamental ways in which we need to understand how signaling process occurs at the atomic molecular level? Forget about the macroscopic level. We need to delve into areas that we're afraid to delve into, which is how does energy transport occur at the quantum level biologically, so we can translate that into the fabrication of machines that are bio-inspired for the future. And those were the types of discussions we had. But what I really want to ask this distinguished group today, and I want to challenge you, is talk to us about what is real. Talk to us about what is possible, and then tell us about what might be in the future. And I do thank you also very much for coming today. Again, enjoy. This is a time of celebration and thought, as Doug has said. Thank you very much.
Thank you, Pat. Thank you, Sherry. My gosh, I'm just going to keep it really short. And those who know me know I have a gift of gab. A long time ago, some people at MIT wanted to use one of my inventions that dealt with distributed operating systems. That's how I first started, was in operating systems theory at Bell Laboratories. But at that time, I was already going over to the dark side of the force. As my dear friend Dennis Ritchie, the inventor of C language, said, "Oh man, we're losing you. You're going over to the machine learning people." Yes, I did. But MIT wanted to use something I invented. I was put on loan to them. I was hanging out with all kinds of great people. Bell Labs was the greatest though, but I was always at that point in time hanging out with PhD students because they were my age compared to the people at Project Athena, where I was doing this extra work with Bell Laboratories and Project Athena. And the PhD students my age were doing AI. I had done machine learning problem, which I thought was really rather cool. And they insisted that I should meet Marvin Minsky, one of the all-time greats. I refused them on their offer because I felt I wasn't worthy. So they tricked me into a pizza night where Marvin showed up. And in October 1986, that's when our friendship with Marvin and his wife Gloria started, and it never ended since then. He had one wonderful, wonderful trait, which I see in a lot of good people like Marvin, Herb Simon, whoever. That's the search for a good question. He would start any class at MIT with, okay, I know we were supposed to talk about chapter so-and-so, but no, any good questions first. And in the short while that I knew Marvin and Gloria, they invited me not to stay at the Marriott anymore. They wanted me to stay at their house over in Brookline. So every morning we'd be up at 10:30 in the morning with a pot of coffee in the kitchen, looking for a good question. And that's what I thought was amazing about these people like Marvin, or like his good friend Richard Feynman, who came to the house every so often. And I just sat there in awe of his friendships with everybody. Randy Davis, his good buddy up at MIT. The hard thing we do is find a worthy question. And then, of course, we try to do our research end result is something that works. I'll talk more about myself later. Let me move now quickly to what we're trying to do today. We are trying, and I really wanted to do this, and Gloria, I know you're out there somewhere with, your other friends up here in Brookline. So a salute to Gloria Minsky. We're trying to follow in the footsteps that Marvin let us have. When Jan LeCun won a Turing Award a couple of years ago, he joked with me, because I know Jan since about 1989. We worked together at Bell Labs in research. He said, yep, I'm following Marvin. And I thought to myself, that's what motivated doing this. This is going to be a series of events. We have a cast of characters like these people. What the people who I work with. Vladimir Vapnik, the inventor of sport basketball machines, and it goes on and on from there. It's a long list. But Jan and I and the team here, Tom, we love Marvin, and I'm sorry. Just trying to show what it means to think. These are not speakers today. These are thinkers. And we're going to argue, which is the best thing we could ever do. The missing part of our argument is we don't have a real chalkboard in front of us, but we'll make do. So without further ado, I wanted to introduce everybody just to say hello. Let me first draw upon someone who won the Junior Award we have at AFOSR. There's a title for the award, but it's just below fellow, and that's Scott Klaus. Scott, will you say hello to everybody?
Sure. Thank you, Doug. I appreciate you letting me partake in this event today. I'm glad to see friends and family here, and looking forward to an exciting round of discussion and some back and forth here today. Absolutely. I'm just gonna hang back and soak it in and take in some questions, and maybe prod at y'all a little bit here after a while as questions come up.
I should say also, Scott is the one who's trying to capture all 1,000 plus of you, your questions for us. I had to find someone who is that good in AI. Trust me, he is that good, and his talent covers many different aspects of AI. So he'll be our scribe this time. He'll actually be one of the thinkers in one of the future events. Scott, thank you. So if we go down the list in the order in which people will think out loud. Next, we have Randy Davis, or Randall Davis, from MIT. Say hello, Randy.
Good day, everybody. Delighted to be here.
Oh, that was cheesy. Okay.
You said make it short.
Okay. Yeah, I did. I'm not good at that. After Randy, we have Jan LeCun from NYU and Facebook.
Hi, everyone. Good morning, afternoon, or evening, depending on where you are.
Okay, cool. Thanks, Jan. After Jan, we have my dear friend for many years, and also known at DARPA as Tom, never mind. Anyway, Tom Mitchell from CMU.
Thanks, Doug. Hello, everybody. Looking forward to the discussion.
Definitely. And Tom has taught us so well. You don't learn just from one math function, but we'll leave that for the argument between me and Tom and Jan and others, because there's machine learning and then there's learning. See, when I stop learning, well, I no longer exist. Continuous learning is the magic that Marvin was after. Next, the most amazing person I ever met. His nickname is Cap, like Captain America. Stephen Rogers from the Air Force. Hey, Steve, Cap, take it away.
Hey, guys. I know everybody's going to ask, what the heck is that picture behind me? My Zoom background. That's how I spend dawn every day with that flunked service dog. He was in training to be a service dog, and we're down at that lake every morning. When we're lucky, we have my granddaughter with me, but that's Napoleon, just so you don't ask later. I don't want that to see that in the chat. Over.
Hey, Cap, we're going to see something about your granddaughter during your talk.
You can't talk to me without seeing a picture of my granddaughter. It won't happen, I guarantee.
All right. And then after Cap, I'm Doug. So let's take it away. Randy, you're first.
Okay, can we get my slides up? All right. I took Doug's charter fairly literally. That is, how are we going to get to 2040 in artificial intelligence? And one suggestion I was going to make is it will be useful to go back to the future. And if my slides could slow down just a little bit and wait until I cue them, that would be wonderful. Anybody got an AI program that can do that? Wait. Okay. I was going to say that almost every day I read another great story about how machine learning has produced some interesting results. Next slide. I'm going to cue the next slide like this. Good. Okay. So this stuff has been astonishingly successful. Every time you turn around, there's another interesting application of the technology. But one of the things I want to do in this kind of talk is take a step back and see where we are. And part of that requires making explicit some of the things that we take for granted. So some of this is about looking around and saying things like, hey guys, have you ever noticed we're living in an ocean of air? We take that for granted. Sometimes it's useful to understand what surrounds us. Now, this stuff has been astonishingly successful, but it's all almost purely data directed. It learns from hundreds of thousands or millions of examples. And data directed, in turn, is a bet that correlations in the world are going to teach us useful information. Now, that bet is paid off in many cases lately. It is a valuable bet. It's been a good bet so far. But there's a caution that's so old that I have to put it in an old-fashioned type font. And that's that correlations are not causality. This, of course, is well known, but as I said, sometimes it's useful to make the important things explicit, even when they seem obvious. We've got to treat this caution, and we got to treat this with great caution, especially as AI gets into applications where errors can have really significant consequences. Next, I'd like to suggest that intelligence is also about modeling the world, more than just what we can learn from vast quantities of examples. And by modeling the world, I mean creating the kinds of things that allow us to understand the world. And if you think about it, understanding is often taken to be synonymous with it fits my model. When I say I understand something, it's because that lines up with my model of the world. But there's more to it than that. We also want to be able to explain and understand what we see. We want to be able to imagine things we haven't even seen yet. We want to be able to problem solve and plan to make those things, to create those things. And we want to be able to build new models as we learn more about the world. I think this is a great list of the things that ought to be encompassed in a broad definition of intelligence. Now, the reason I can admire this list is because I didn't create it. It actually comes from Josh Tenenbaum in one of his talks. And I've borrowed it whole cloth, but there, at least I've cited it. I think it's a very good list and a good way to stay broadly focused in the task ahead of us. Now, there's a great deal of talk about transparency, particularly with respect to the machine learning systems, but also with respect to other systems as well. I want to remind us that transparency requires communication. Communication, in turn, requires a shared language. And the early expert systems and knowledge-based systems, simple as they were, had a degree of transparency because they were capturing what human experts knew about their task That is, they used the concepts that people had, and as a consequence, simply replaying some of their logic provided a primitive but useful form of explanation and transparency. Now, in that sense, I want to claim that deep learning systems are alien intelligences. They're alien intelligences because they have invented their own way of thinking about the world, often based on features that are useful to discriminating between positive and negative examples. But are those features the kinds of things that we use to understand the system in a way that goes beyond capturing classification kinds of tasks? Now that brings us back to the suggestions that humans can provide, next bullet, please, that human ontologies can provide the needed vocabulary. If we're going to understand these systems, I think they need to have a vocabulary that we have. They need to understand how we understand the world. And yes, we'll adapt to their vocabulary as well. And there are instances where this stuff is overlapped. In some of the convolutional neural networks looking at images, for example, we've seen instances in the middle of those networks that seem to be edge detectors. And in face detection systems, elements that detect eyes and noses. But we want more than that. We want more than just shared patterns that we might recognize. We need a vocabulary that matches the kind of vocabulary that we use to understand the world. Let me make two other observations that have been with us for a while. First of all, it's remarkable how people learn from very few examples. Now, this, of course, isn't unnoticed. There's a lot of interesting work aimed at this at various places, but I think it's a very important problem and a key mystery to attend to. And to the extent that this talk is about what's the next big question or questions, I think this is one of those very big questions. And again, it hasn't been ignored, but I think it's absolutely key and we need more attention to it. Imagine if we didn't have to round up a few 100,000 or a few million examples in order to teach the computer something, in order to teach our system something. One other comment from the early years of AI is the answer to this astonishingly simple sounding question, which is, why are experts good at what they do? For cognitive tasks, it appears that the answer is in large measure simply that they know an awful lot. From medicine to chess to tasks in biology, chemistry, and so forth, experts know a great deal, and that appears to be an important source of their ability and a source of their expertise. And what works for us is likely to be useful for our programs. It would also give us another basis for communication. Let me finish up with some forward-looking suggestions about what to do next. I think we ought to reconnect to and rejuvenate the work on knowledge representation. Now, this has started to happen in some ways. I know some of the really interesting work on drug discovery using machine learning techniques has benefited from even the simplest model of chemistry. It didn't learn that model of chemistry. It was given a simple model of chemistry, a ball and stick model, chains and rings and so forth. And that enabled it to be much more guided in its search for relevant kinds of molecules and made the progress considerably faster. So sometimes even simple bits of knowledge representation, symbolic knowledge representation, coming from the people who have that in their heads can be extraordinarily valuable. Which leads me to the next suggestion. Another direction that is, again, in progress, but I think needs additional attention, is to marry the data-directed AI of today that is succeeding in large numbers at many different tasks with the power that comes to the kind of symbolic knowledge representations that we have in our head. It's useful, I think, as before, because it gives our systems something else to know about the world, and that knowledge can help them. It also provides one of the foundations for communication, because once again, to the extent that we have a shared vocabulary in that knowledge representation, that will give us one route toward transparency. And finally, I want to suggest that programs should learn from data, reading, being told, and any other goddamn thing we can think of. And I know we will hear about some of these later this afternoon. But part of the idea here is a multiplicity of techniques is always a good idea. And we do that. So why don't our programs? And with that, I'm finished. Thank you.
Okay, Randy, that was great. I also like Josh Tannenbaum, Josh's pointer you gave for everybody. He'll be one of our speakers, no, sorry, thinkers at our next session, because we have a rather large team of about 38 people. These are just a few of them, but they include many different people like Vladimir Vapnik and Josh Tannenbaum and so forth and so on. So we'll have plenty to keep us busy during the year. Every other month or so, we'll do this. I forgot to say that the way we are structured, each person will present some interesting ideas, some thinking, and that'll be about 7 or 8 minutes. After which, another 7 or 8 minutes will be spent by the entire group of thinkers interacting with each other about what was said. So let me turn it over to Jan and, oh my gosh, you hit everybody. It wasn't just, the data specific. There's things about Nell from Tom, and go at it, you guys, and I'll jump in whenever I can find a space.
Hey, Doug, can I start the volley?
You got it.
Hey, Randy, I just love that, by the way. I tell you, one of the things that I've been struggling with, and I'd love to hear your ideas on, when you talk about marrying these multiple ways to represent knowledge, we struggle to see, how does nature do that? Are they done sequentially? Are they done in parallel? Do you envision one making a decision and the other defers? Or do you expect it to be a mesh? What's your thoughts in that? Over.
First of all, I don't have an answer. Let me acknowledge that at the beginning, because I think this is one of the great and pressing problems. And if I had the answer, I'd have given a different talk. But I don't have the answer. So let me fill you with my biases. I think questions about parallelism and sequentialism are at the wrong level. I think what we have to think about is, how does the fantastic ability of our machines to detect subtle patterns in data in the world somehow get linked up to the level of abstractions that we normally think of? So it's connecting those two kinds of things. How do I tell a machine learning problem? How do I tell a machine learning system that's discovering new antibiotics, as happened a year or two ago? How do I tell it about enough chemistry that it can supercharge its ability to discover new molecules? That would be wonderful. And I don't know how to do it, but I think it's an important problem.
Yeah, I see you, Tom. Go for it.
Okay, so I like, Randy, what you're saying, and I just wanted to take maybe 90 seconds to ground one of the points that you made that I think is really important. You pointed out that people learn from sometimes very few examples compared to computers. And I want to give a very brief example of where we can see people learning very quickly, and we can understand how they do it and see the difference with machines. So here's the example. Suppose you're learning to play chess or even tic-tac-toe. Often, for example, when you're learning to play chess, if you lose your queen, it doesn't take you thousands of examples to learn that, or even to learn how to avoid it. If you're playing chess, and let's take the problem of learning the concept chess positions where I'm about to lose my queen. If we wanted to train a neural network or some kind of statistical learning algorithm to learn that, we would presumably have to show it thousands of examples of chess positions where you are about to lose your queen, and then thousands of negative examples where you're not about to lose your queen, and have it work out the details. But people learn it in 2 or 3 examples, because they stop and they reason about what just happened. They say, why did I lose my queen? Oh, I see. The reason I lost my queen is that my opponent was attacking my king and my queen at the same time. And I had to move my king, and therefore it was their turn, they got to take the queen. That little chain of reasoning, which is the kind of stuff that even current AI can do, allows the learner to then notice that what features of the board were involved in that reasoning, in that explanation. And it turns out the only pieces that were discussed in the explanation were the king, the queen, and that other piece, maybe a knight, that was attacking both of them simultaneously. The explanation never mentioned the position of the 14 pawns that are on the board, and therefore they're clearly irrelevant. We can generalize away to first order, we can generalize away what those pawns were doing. That kind of reasoning is what people do as they're attempting to learn from some experience. What's the general reason that this experience is going to happen? And therefore, what's the general pattern they want to avoid in the future? So I think, historically, there was a line of research in machine learning looking at this kind of use of reasoning and explanations. It hasn't panned out. And I think part of the reason is that AI is not today really very good at reasoning about systems, except for systems like the one I just brought up, a game where we know precise rules of the game. We can predict flawlessly and deterministically the effect of each move. But in the real world, we don't have that. But still, I wanted to bring it up as a kind of an example to ground some of our thinking about what might be going on in people that allows them to learn with such few examples, and what we might aspire for AI to do.
Yeah, I think, let me make just a couple of brief comments about what you said. First of all, I think one of the reasons people do as well as they do at chess, which is not very good in the beginning, of course, is they have behavioral models or functional models of the pieces. The thing about the queen is the multiple directions it can move in, and you know that. You don't have to learn that. That's part of what you're told ahead of time. It's not like, here's a bunch of chess games, figure out what's going on and then figure out how to win. It's here are the rules, and the rules offer an enormous amount of guidance. The other thing is that strikes me is the explanation you gave was a causal explanation. The reason I lost my queen is because this caused that, which caused this. The knight caused me to pay attention over there, and then this piece was able to do that. Constructing causal models of the world is very important. It typically, to give Jan an easy opening here, it typically starts by noticing correlations. I mean, where do we learn our unfamiliar and new causal models? Sure, we start with correlations, but we need to get beyond that. And again, this is not a brand new insight. Judea Pearl's book on causality and lots of other people working in this area. I'll just, again, all I'll do is underline that and say, I think that's another important area of future research. Anybody else want to take a shot at me?
Come on, Jan.
Well, I'm going to do that, in my segment. So I'm holding it back at the moment.
He's holding his ammunition. That's all right.
Minutes. I was thinking about the reasoning piece, and reasoning about games, especially some of the different, more recent work that's been done out at Google, is really good stuff. A very dear friend of mine, Murray Campbell, was one of the IBMers who did the Deep Blue Casbah work. But there's something I would ask you, and this was brought forward by a friend of mine at AFOSR. Okay, great. So we can get all the knowledge of what it takes to play chess or Go. But an example he gave was an example that Richard Feynman had. And it might have been an argument he and Marvin had, because he and Marvin were very close. And they did a lot of neat things together that, you know, if you go to Marvin's house, you'll see Richard's bongos on a shelf there. For those who know Richard really well. Here's a problem. A person from another planet comes to Earth. He sees what appears to be, we would know it as a soccer field with the players playing something. But the soccer ball is invisible. So you see certain causalities happening by the actions of the actors and other objects in this game. And the goal, of course, is to learn it in 1 or 2 moves, not 10,000 bits of data, 1 or 2 bits of data. The classic Josh Tannenbaum view of the universe. I will learn that with one example. Now, think about that. Call me up, send me an email. That's a good problem. And Tom would know this because we talked about a problem that he and Marvin were doing at NASA many, many years ago. He would say, well, now that's a good question. So I'm going to keep pushing the envelope out of the far end. I live on both sides of the coin. I really believe in the MIT mascot. It's the beaver. It's an engineer. You have to build it. You have to find that people can use it, or why bother? On the other side of the coin, not engineering, but thinking about it from pure theory is also important. So I pose this as a question for the year 2040. I don't want to lose sight of either side of the coin. I love building stuff and having it go all the way out to the end user. I did that through my entire career. But you also have to sometimes hop in a rocket ship next to Marvin and go way out into space and think. Go ahead, Randy.
I just wanted to make one more comment before we move on this learning from few examples. And again, this is not novel, but I think it's worth remembering that we learn quickly because we know so much already. If we abstract your soccer game example even further, and I show you a rectangle with a bunch of dots moving around on it, and I ask you to make sense of it, and there are no goals, and there are no ball to kick around, and all I want you to do is make sense of this pattern of moving dots, you probably won't. But when we bring to bear knowledge of it's a game, there are 2 sides to a game. People on the same side try to help one another, et cetera, et cetera, et cetera. That's what allows us to get somewhere with that task.
Yeah, I've seen that example from Josh showing us that idea.
Yep.
That's a good one, really good.
It's sense making. And I think the significance of sense making is underestimated.
Oh, well, now you just hit the hot button. If I think about 2 wonderful buddies, John McCarthy and Marvin Minsky, common sense reasoning, my gosh. Well, anyway, year 2030, moving towards year 2040, and we got to do things all along the way. Let me turn it over to you, Jan, and talk to us about world models.
Well, so this is going to echo some of the stuff that Randy talked about. And, you know, I agree with 90% of what you said, Randy. So I was not holding back my ammunition. It was just my flowers, if you want.
Can I make one quick comment for the audience's benefit? The 4 of us put together our presentations entirely independently.
Yes.
So any interesting overlap or contradictions is just going to be fun. We didn't plan this.
We didn't plan. We didn't know what each other was going to say. Right. So I think one of the main obstacles to making true progress in AI is to get machines to learn world models, because I agree with what Randy said previously, that the essence of intelligence really is the ability to understand the world, predict what the world is going to do because the world is being the world, or what the world is going to do as a consequence of our actions. And this is kind of connecting with the idea of causal inference. And so how do we get machines to learn world models, to figure out how the world works by observation, the way young children appear to be able to do? Next slide, please. So in fact, I see it says 3 challenges, but it's really 2, because the third I didn't list. First, because I didn't have enough space, and second, because I have nothing to say about the third one. So I'm only going to mention 2 of them: learning representations and predictive models of the world. This basically is the idea by which, by observation, young children of a few weeks or a few months old observe the world and figure out within the space of a couple of months that they are inanimate and animate objects, and they can tell the difference. They figure out that when an object disappears behind another one, it still exists, object permanence. They figure out after 8 or 9 months that objects that are not supported are supposed to fall. So basically the notion of gravity, and then things like intuitive physics of inertia and things like that. That takes about 9 months. And it's not any kind of learning that we observe that we know about in machines. It's not reinforcement learning, it's not supervised learning. It's another type of learning that we don't really know the nature of it. I call it self-supervised learning because it's a hypothesis about how this might be done. And I think if we can get machines to learn world models by observation, and perhaps also with a little bit of interaction, we'll make significant progress towards getting machines that can learn from a small number of examples, which is one of the main problems that Randy was just mentioning, which I agree is a huge problem today. And also machines that can acquire some level of common sense by basically experiencing the world and having, and building a world model. So if you do have machines that have world models, they can use this world model to predict what's going to happen, for example, as a consequence of their actions. And that allows them to plan. So this is what Daniel Kahneman calls system 2 reasoning, which is, you don't instinctively react to a situation, but you kind of think ahead about, what you might do, and then pick an action or a sequence of actions that will result in a particular outcome. And the nice thing about this is that mathematically, you can basically reduce reasoning to essentially optimizing a function, an objective function of some kind, with respect to a sequence of action. The same way machine learning minimizes an objective function with respect to parameters of a system. So what is self-supervised learning? Self-supervised learning, basically, the simplest form of it is just predict the future. Here is a segment of video. Tell me what's going to happen in the next fraction of a second, or maybe in the next few seconds, in the next minute, in the next hour. And of course, to predict what's going to happen in the next fraction of a second, you don't need to know much about how the world is constructed. You need to know how pixels move, right? This is what your video compression system that is currently connecting us is doing. But then if you want to predict longer term, you have to understand that the world is 3-dimensional, that there are objects that can move independently. There are inanimate objects that follow known trajectories, and animate objects that follow trajectories that are more difficult to predict. And the longer term you're trying to predict, the more abstract the representation has to do, and the more complex the uncertainty about the prediction is. And that's where the crux of the problem resides, which is at the moment, we don't know how to represent uncertainty in prediction for data of the, data that is of the type of something like a video. We know how to do it for text. And in fact, self-supervised learning works really well for natural language understanding at the moment. It pretty much revolutionized natural language processing over the last 2 years. But not so much for images and video and things like that, so far, at least. So that's kind of a challenge. Now, it's not just predicting the future, it's just predicting whatever you're not currently perceiving, right? So your perception system that gives you an idea about the state of the world, you might want to use it to predict what's going to happen in the future, but you might also want to use it to predict what happened in the past that you didn't observe. Or perhaps you're currently only seeing the front of my face, but you probably have a good idea about what the back of my face looks like, because because you have a good model of what humans are supposed to look like all around. So I think those are the two main challenges. The third one, which I didn't list here, is learning hierarchical representations of action plans. And I have no idea how to do that, so I didn't put it on the slide. Next slide, please. Okay, so there is really, as I said, the main issue, I don't want to get too technical, but the main issue with self-supervised learning is representing uncertainty in a prediction, right? So you're seeing me talking at the moment. The next thing I could do is I could do this with my hands, or I could move my head to one side or to the other. And if I ask you to make one single prediction, which minimizes the expected error of what actually is going to happen, the best thing you can do is predict a blurry version of my face that moves to the left, to the right, and my hands also blurry, which is not a good prediction. And so you had to have some representation of the plausible futures that may happen. And how do you do this in sort of high-dimensional continuous spaces like the space of video frames or images? So there are really two models. If you base this on the kind of general framework of deep learning, one type of model, or even if it's not deep learning at all, actually, one is you represent uncertainty through a latent variable, and when the latent variable varies, the prediction varies as well. And the other one basically gets around the problem of predicting altogether. It says, I just want to find a representation of the world in such a way that the internal representation of the thing I need to predict, the future, let's say, is predictable from the internal representation of what I observe. Okay, I don't want to predict all the pixels of the future frame, but I'm going to compute some representation of the past of the video and the future of the video, and I want this one to be predictable from that one. Okay, it's a much simpler problem in a way because I can choose to ignore a lot of details about the world in that scenario. And I used to be a big fan of the thing on the left, and over the last year or so, I've kind of completely switched to the thing on the right because I think it's more promising. Next slide, please. And in fact, I'm not the only one. Probably one of the most exciting set of progress over the last year or so in computer vision in particular, but in machine learning more generally, is the idea of joint embedding methods. So those ideas where you have basically, the thing you're observing, the thing you're trying to predict, and you're trying to find a joint embedding of those two things so that the code of one is predictable from the code of the other. So there's contrastive methods for this. I'm not going to go into the details of what that means, but those have been around since the 1990s. In fact, since the days that Doug and I were at Bell Labs, and I was working on something to do a signature verification, and we basically came up with those methods. Jeff Hinton had similar ideas around the same time. If you go to the next slide, I think what has been really interesting over the last year or so is that a new set of such methods have appeared that I would call non-contrastive or regularized joint embedding methods. And I think this is the ticket. I think this is the most exciting thing that has been happening in machine learning over the last 10 years, frankly, if not more. And so this could be this type of method, maybe not those particularly, but this type of method may be the ones that will take us to the level that we'd like for self-supervised learning, sort of generalized self-supervised learning, where we can learn machine to learn how the world works by observing videos. Now, next slide. Now, if we had a way to train machines to learn models of the world, we could put this into some sort of autonomous intelligent agent, right? So the components of an intelligent agent are a perception module that basically estimates the state of the world to feed the world model. Then you have the world model, this green blob here, which basically, given a hypothesized action and hypothesized state of the world, predicts the next state of the world. Okay, and you can feed it a hypothesized sequence of action and get basically a internally simulated sequence of states of the world. And then you may have an internal system that measures the quality of that state of the world. Does it fit what you want to achieve in the goal essentially that the system has? And that is represented by some sort of cost function or a critic or something like this. So a critic if it's trainable, a cost if it's hardwired. We have all those things in our brains, actually, brains of animals are kind of built on that model a little bit. And then when you sort of unfold a session, if you want, of that system, what you get is something that's very similar to what people do in optimal control, where you again have some estimate of the state of the world. You have a world model, which usually is built by hand, it's not learned. And then you have a cost function, which is how far your rocket is from the space station or something like that. And then you try to figure out a sequence of action that will kind of minimize the cost according to your model of the world. So the complexity here is doing this where the model is learned, where the world that the model is modeling is stochastic, non-deterministic, where the cost may not be that easy to come by. But that's basically the architecture of an autonomous intelligent agent. The piece we're missing is how do we train world models? So that is, in my opinion, the most interesting question at the moment in AI. We were asking you about question, Doug, right? That's a question. How do we get machines to learn world models? And with that, I'm done.
Thank you very much, Jan. Tom, go ahead.
Hey, Jan, I totally agree that learning world models is important. One of the questions that I have, and I wonder if you think this is an open or a closed question, is how to deal with time. And you mentioned that we inherit a lot of these ideas from control theory, and now we need to sort of use more modern AI techniques to substitute parts. But one of the assumptions in control theory is that there's a clock.
Yeah.
And that things move forward tick by tick by tick. And what it means to predict the next state is to predict the next tick. And as you said at the beginning, if tick is small enough, then the next state is pretty much like the current state, sure, except for optical flow or something like that. But if if I'm in a state where Doug tells me he's headed to the airport, my future prediction is Doug will get in his car or maybe take a taxi or an Uber, but then he'll end up later at the airport where he will check his bags and do stuff. But that prediction is not locked onto a clock. Yep. And in a way, it's a partially ordered sequence of future states. That's right. And so the question, to turn this into a question, what is the next thing? What is the target of the world model? What is it that we're predicting? Is it the state at a particular time? Is it a partially ordered sequence of future states? Is it something else?
Right. So I think it's one of the most important sub-questions in the question I asked. And I totally agree with you that it's it's a huge question to answer before we can make progress. So I think if I want to go and chat with you in Pittsburgh, how do I plan this, right? I mean, first I figure I have to catch a plane, right? So I have to go to the airport, catch a plane, then grab a taxi or something, and go to your place. And then I have to, how do I get to the airport from here? I have to get out of my house. I have to remember where the door is. And then I have to decompose this into millisecond by millisecond muscle control. So obviously there are several timescales and several levels of abstractions for the description of the various the various actions or the situations or the states of the world, right? So the same way, in convolutional nets and deep learning, we're able to train machines to learn hierarchical representations of the world or the perceptual world, where at the low level we have edges, and then we have combinations of edges and motifs, and then we have parts of objects and objects, etc. We need to have some way of building and training world models that are hierarchical in the same way. So they can predict at a short time scale, but sort of high bandwidth information at a short time scale. And as we train them to predict at a longer time scale, then the level of description that they have to use has to be more and more abstract and kind of abstract away a lot of details that are irrelevant to the situation. Now, how to do this in ways that are as automatic and natural as the way convolutional nets, for example, learn perceptual representation is not clear, but it will probably involve something like temporal subsampling. So the fact that every time you go up one layer of abstraction, which may be layers of a neural net, you also kind of do temporal subsampling. So now the step, the clock at which you run your predictor is now much slower. So that would be how I would approach the problem. Like how precisely to do it, to instantiate this, I don't know yet.
Can I jump in on that? I am always very friendly to things, and Herb Simon, in his book, Sciences of the Artificial, talks about the importance of hierarchy. The old version of the book is, I think, chapter 7. I think now it's chapter 8. I'm not quite sure, but yeah, you need hierarchy for systems to do what they do. But a Minsky argument is you don't want hierarchy all the time. And those who know me very well know what I'm about to say. What you really want is fluidity, which means heterarchies. Heterarchies that allow you to move between different levels of abstraction. Oh, by the way, that's for you, Colonel Havey. You were asking about abstraction. Were we going to get to it? Oh, we will. But the system has to flow in and out all over the place at different levels based upon what would be perceived as conscious thought. I'm introducing some wrinkles now, but they play off of where Marvin thinks. So we have to have hierarchy in order to make progress on systems that we can make work right now that are relevant to people, the Air Force or whoever. But in the theory of what we're trying to do, I think Marvin's right. Hierarchies are very valuable, and I'll talk about that in a little bit in the way that he uses trans frames for causality. He integrates his idea of frame theory with conceptual dependency CDs from Schenck and his students back at Yale that ties together the trans frame, A trans, P trans, different structures. These are mental structures that are tied into then filling the slots in the frame at a single nanosecond of time. But that's okay, because we have 7 plus or minus 2 different sets of slots. Of course, my students from Rutgers, who I used to take down to Princeton to see George Miller, George's joke was, why did God give us just 7 plus or minus 2 short-term memory systems? Why not 100? But Simon resolved that with his paper on how big is a chunk. So there's a lot of good stuff we could do with a theory today. There's a lot of good stuff we could ask good questions about for the year 2033. And again, I will push Marvin's envelope of the year 2040. But the point here, Jan knows me too well. We need hierarchies and we need hierarchies. I'll stop there.
I agree with that.
Yes. Okay, Tom, show us this wonderful story, which really has a lot of meat behind it. It's really good, people.
Okay, so I think the first time I discussed with Doug this upcoming meeting, every time I discuss with Doug, I get a slightly different picture of the elephant or piece of the elephant. But the one that I latched onto from an early discussion was the question is, what is AI capable of becoming by 2040? And what will it take to get there? So in thinking about how to organize my thoughts, I thought I would try, and in the end, I came up with 2 breakthroughs in AI that I believe are achievable by 2040, but not guaranteed. It will take some serious thinking and work. But I give them a better than 50-50 chance. I'll go on record saying that. And I think either of these breakthroughs, if they were to occur, would make a fundamental change in how we think of AI. And if they both occur, I think it would kind of fundamentally change the nature of how we interact with computers. So I want to try this out on this group of thinkers. The first breakthrough would be if we could routinely build AI systems that are continuous learning, continuous learners, and cumulative learners. So let me say what I mean by that. When I say continuous learners, let me just draw a contrast to 99% of what machine learning systems we have today are what I would call a 2-phase system. There's the training phase where, for example, if we're training a system for medical diagnosis, we go back and get our historical data and we train the diagnosis system to look at the symptoms and predict whether the patient has COVID. And then we do the fielded use part of it. So it's train and then stop learning and start using. That's most of what we have these days. There are some examples of continuous learning that don't do that. And a good example is a spam filter. A spam filter can be retrained every night because you keep getting more and more data about what users consider to be spams. You can keep retraining it. So I would say that's a continuous learning system, but it's not a cumulative learning system. What it's doing is using the most recent data to replace the learned function it had yesterday with a new one for today. So I would say it's continuous, but it's not a cumulative thing. It's not building a world model and learning from that, for example. So now if we think about humans, which is my favorite heuristic for predicting the future of machine learning, we notice that people learn continuously, but cumulatively, in the sense that there's a curriculum. First, we learn to crawl, then we learn to walk. We couldn't really walk until we learned to crawl. Then we learned to run, then we learned to ride a bike, and so forth. We learn to count, and then we learn to add, then we learn to multiply, then we learn algebra, calculus. So we learn cumulatively in the sense that once we have learned something, we suddenly become better learners. We become positioned to learn something that we couldn't have even learned before. And that's what I mean by cumulative learning. Think of it, it's related to having a curriculum of going from learning simplest things and progressively more complex. So that's the breakthrough that I would say, breakthrough number 1, that I hope and believe we could get to by 2040. And let me give a very brief example of some research from our own group, a system that we call our never-ending language learner, or for short, NEL. It's a continuous and cumulative learning system that tries to learn to read the web. So NEL ran, we finally stopped it, but it ran for 8 years, 24/7, trying to, no, I'm not moving on to that slide next. Thank you. But NEL every day had 2 tasks to do. One was to extract more beliefs, factual knowledge from the unstructured text on the web. And the other task he had was every day to learn to do task number 1 better. That is, learn to read better than it could yesterday. the evidence for that would be if it could look at the same text that it looked at yesterday, but get more accurately more facts from it. And so Nell actually did succeed in a particular way to be a continuous cumulative learner. If you look at what it did over those 8 years, you see that it first worked on the task of learning to classify noun phrases according to what type of entity do they refer to. If there's a noun phrase like Doug Ryken, that refers to a person. If there's a noun phrase like love, that refers to an emotion. If there's a noun phrase like baseball, that refers to a sport, so forth. So first thing it did was focus on the task of cataloging all the noun phrases it could find according to what semantic category, what kind of entity do they refer to. Once it started to have some competence to that, then it became able to start extracting from the web relations between pairs of noun phrases. And it was given a set of relations like person founded company. And after it knew about Bill Gates and knew about Microsoft, it was able to determine from the text on the web that Bill Gates founded Microsoft and lots of other relations. So first the entities, the noun phrases, then the relations between them. Once it did that, it actually had the ability to discover new relations we hadn't told it about, because it would find these statistically surprising co-occurrences, for example, of certain type of people and certain types of musical instruments. Ringo Starr appears a lot with drums, Eric Clapton a lot with guitars. And so it would invent additional relations we hadn't told it about, like person plays musical instrument. So that's kind of a third layer. A fourth layer, once it had read enough of the web to have millions of beliefs, then it could data mine that database that described that knowledge base that described the world it was reading about, and it could learn to predict new beliefs that it hadn't even read. So for example, it noticed in its knowledge that if some athlete A plays on team T and team T plays sport S, then with high probability, athlete A plays sport S. Once it learned that just by empirical regularities in its knowledge base, it could predict new beliefs, like Mickey Mantle, who plays on the Yankees, must play baseball. So I just give that as an example of what I mean by cumulative learning. Here's a system that's learning multiple types of skills, but in a sequence that necessarily, a necessary sequence in a way. You could never have started learning the rules to predict new beliefs it hadn't read until it could at least read some relational triples from the web. And it couldn't do that till it could at least spot noun phrases. So that's the kind of machine learning that we don't see today, but I think it's within our grasp. Systems like Nell and a few others are moving in this direction. Why do I think it's an important breakthrough? Because in so many ways, that's what's limiting the applications of machine learning for us. So for example, just to think about what would be possible if we had that. Imagine that you could have a cell phone with cameras, microphones, speaker, and a display with that kind of continuous and cumulative learning method embedded in it. And you could stick it in the ceiling you could stick it anywhere you like and have that system learn 24 hours a day expertise about that particular room or location where it was. If you put one of these in a medical patient's room, what would it learn? Well, if you think back to the sequence of things Nell learned, analogously, first it could learn to detect the different kinds of objects and people in the room. What are the entities? Like, what are the noun phrases and what are types of them? Then relations and actions among them. Usually the nurse pushes in the table with the food. Usually the table contains food on it. Sometimes the table has medicine on it. The patient usually eats the medicine and the food, and so forth. So once it knew what the objects were, then it could be positioned to learn regularities about relations and actions between them. After that, it could again, after it built up enough of that kind of understanding, it could move on to learning to predict what's going to happen next, the kind of world model that Jan was talking about. And then it could be very useful as a kind of assistant to the patient, because it would have learned that when the patient gets out of bed, they usually walk to the door, but they don't usually lie down on the floor on their way. And if that were to happen, there's a good reason to give an alert to the nurse. Okay, so that's breakthrough number one. I'll just say it's continuous, but importantly, it's not just continuous learning, like a spam filter that retunes itself. It's cumulative, like us, that once it learns X, it's in a position to be a better learner of Y. Okay, second breakthrough, if I still have time, do I, Doug?
Yes, go ahead. Come on, Tom.
All right. Second breakthrough is machine learning by human instruction. So Randy mentioned this in his remarks at the beginning too, that people learn in a lot of different ways. He put on there learning by being told. A lot of learning that humans do is based on instruction. And now that over the past 5 years, we suddenly have competent conversational systems like Alexa and Siri and so forth as kind of primitive, but at least we can talk to them. There's no reason not to expect a new burst of research in machine learning by instruction. Now, if I can move on to the movie, I would like to. And here's just to give you an example. Before we start the movie, can we go back to the beginning of the movie?
So it's just this,
Okay.
the frozen.
Okay.
Yep.
Gotcha. Okay, so what I want to show is a movie produced by Toby Lee, one of our PhD students who graduated earlier this year. But the research he was interested in was, what if we make it possible for people to teach their phones new functionality by instruction? So the way I like to think of it is, if I ask you how many people on Earth today can program their phone to make it do new things, the answer is surely less than 1%. Those are the people who have learned, put in the time to learn the programming language of the computer. But instead, by 2040, why don't we get rid of programming languages by making computers learn the language that people already use when we instruct one another? And so I want to just show you this quick movie from Toby where he teaches this phone, in this case, that whenever he asks it to get a coffee from Starbucks, if it's hot outside, it should be an iced coffee. And if it's not, it can be a regular coffee. But you'll see, what you'll see is him showing and telling through verbal instruction plus gestures and demonstration, essentially programming this new capability into the system. Please play the movie.
If the weather is hot, order a cup of iced coffee.
How do I tell whether the weather is hot?
When the current temperature is above 70 degrees Fahrenheit.
I think what you meant is, the value of a concept current temperature is greater than 70 Fahrenheit. Is this correct?
Yes.
How do I find out the value for current temperature? You can explain or say demonstrate to demonstrate.
I will demonstrate.
Please start demonstrating how to find out the value of current temperature. Click OK to continue.
So how do you find the current temperature? You open the
Want to
weather
record
app.
the operation. Do you want to record the operation? Set value of, okay, I learned how to find out the value for current temperature. Okay, I learned how to tell whether the weather is hot. How do I order a cup of iced coffee? You can explain, or say demonstrate to demonstrate.
I'll demonstrate for you.
Please start demonstrating how to order a cup of iced coffee. Click. Do you want to record the operation? 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 Click on the item. Do you want to record the operation? Click on the item. Okay, I learned how to order a cup of iced coffee in Starbucks. Should I do anything if the condition, the weather is hot, is not true?
Order a cappuccino.
I've finished resolving all concepts. Below is the updated list of existing knowledge. I've understood your instruction. If the condition, the weather is hot, is true, then perform the action, order a cup of iced coffee. Do you want me to execute it now?
Yes.
Executing the script. The value of current temperature is 86 degrees. The condition, the weather is hot, is true. Executing the procedure, order an iced coffee.
Okay, so I'm sure you get the idea of what Toby is up to there. But my point is that that kind of instruction is something that people don't need to learn. We already would do that if you were teaching me how to do that procedure. The barrier between most people and getting their phones to do what they really want them to do is that they don't know how to program. And even if you did it, it's a big hassle. If we could, by 2040, get to a position where, say, 80% of computer programming could be done by showing and telling, we would democratize programming so that suddenly we'd have everybody on Earth able to do at least some kinds of programming. That would lead to a burst of creative programs that we haven't seen before, is my guess. But now that breakthrough combined with the other one of machine learning that learns continuously and cumulatively, I think is a very, very powerful combination. Go back to that cell phone that we glued to the ceiling of the hospital patient's room. It was already, from passive observation, able to learn the objects and the routines, the relations that occur typically between objects, to learn to model the world and predict the future. If you add to that the ability of the patient to instruct that agent in this way, and also for the nurses and the doctors to instruct the system and to have a conversation about what the goals of the patient and the medical team are, I think you have a very powerful combination. And I'll just end by pointing out that if you think about that hospital scenario, there was nothing about the initial equipment. It's just a cell phone with cameras and microphones and displays that says it had to be a hospital where it was fielded. Another copy of the same equipment could be put in a Starbucks, and it could learn the routines in Starbucks, including the fact that usually when people get up to leave, they depart the table, but they don't leave their purse on the table, and they don't leave their cell phone. And that an anomaly would be if somebody did that. And then furthermore, through instruction, it could even be aided by helping to teach it that that's something you'd like it to spot. Okay, so I'll end there. I think you get the idea. These two breakthroughs, I think, are both within our grasp, but it's going to take some, let's say, I think, retargeting of research effort a little bit, which can be persuaded by groups like AFOSR to push in these directions. So thanks.
Sounds good. Hey, Cap.
Yeah, buddy.
What do you think?
My response, and Tom, as always, thank you. We've had this discussion about DIY AI. So the idea of do-it-yourself AI by the non-AI expert, that's clearly something that we care a lot about. I was going to ask if it would be commensurate with your thoughts for us to add on to that. The example you gave is, I'm going to say limited to humans teaching a computer, but where I would like to go, I've heard Jan and others talk about sources of knowledge and how machines are dominating the creation of knowledge going forward on the earth. And when you look at where knowledge comes from, either from experience or evolution experience or culture, my question to you is, can we add to your list of machine created capability and knowledge, machine to machine culture? In other words, I can imagine the bot that you create and the bot that Jan creates communicating with each other, not understanding the background, but coming up with a scaffolding of a world model, being able to share knowledge in a culture-like way. Over.
Wow. Great thought. Two reactions. One is, if Jan and I are using the same programming language, then maybe his communication to my program could be more straightforward than that. But thought two is, if we're not, then maybe this kind of show and tell programming would be the method of choice for one program to teach another. I know it's not something I thought about, but I love the idea. What do other people think?
Go ahead, Randy.
Tom, wonderful work. I have a couple of questions. One question, one pushback. Why did you kill Nell?
Yeah, we killed Nell because it became, well, there are two reasons. Number one, it became a software engineering nightmare. It was built out of the PhD theses of about 7 students who had moved on. But the second reason was, I think we learned what we were going to learn about the architecture. The real research question is, how do you architect a system so that it can successfully learn continuously and cumulatively? I think we learned what we were going to learn from that experiment. And what I want to do is launch a new experiment instead.
Yes. Okay, good. Your first mistake there was letting the graduate students go. Never do that, because then you can't run their software. Second, I want to push back a little on this example from Pumice. This is programming by example, right?
Well, more than that, because there's a conversation going on.
Yeah, okay, so it's interactive programming by example, but it's going to inherit all the difficulties of programming by example, which is how broadly do I generalize? How do I know how broad a lesson to learn from the example? That's one thing. The second thing is, it sounds to me like this works well for Alexa level skills, but what happens in the real world where, you know, if I'm on the road in Montana and it's 20 degrees and you know, the notion that people are going to be able to teach their phones complicated things. No, the notion that people are going to be able to teach their phones something more than straightforward tasks, and there's nothing wrong with being able to create straightforward tasks, is, I think, ignoring the complexities inherent in the real world. Never mind the programming language. How do I even express in English all the complications?
Right. So I actually agree with all those critiques. That one thing I would love to do is get a better list of examples of where this kind of show and tell programming based on a system that already has some utilities in it. And what you're really programming is how to string together and give the right arguments to these different utilities. And one example I'd love to figure out, if there are people in this audience who could help, is, for example, what if you had an engineer, a maintenance person working on equipment, and they have their own equipment like oscilloscopes and so forth. Is there a scenario where that engineer could be helped, that maintenance person could be helped by being able to customize, in the kind of way that we were just seeing Toby do, their system? So for example, they might say, if you're communicating with me on the airstrip and it's too noisy, then flip from verbal communication to the display. It's a simple thing, but it's the kind of thing that an individual might want to do. More interestingly, maybe there are examples where they would like to say, if you ever detect this set of symptoms in the equipment, then perform this procedure, or at least send me an alert. So I'd love to brainstorm with people to find some more examples outside the phone for this kind of stuff. One thing I'll say about your comment that this touches on all the shortcomings of programming by demonstration. I do believe that natural language gives us a big lift on that, because if you can only demonstrate,
yeah,
you can't say anything about how to generalize. If you can demonstrate and speak at the same time, then you can say, well, right here, I'm pulling down the menu and I'm clicking on iced coffee. But I could have clicked on any of those things on the menu. You could say that. And then when you go to pay, you could say, I'm paying with my logged credit card, but I could pay with PayPal or Apple Pay. So there could be verbal ways of introducing hints about how to generalize.
But then we're back in the classic confrontation between the lovely ambiguity of natural language and the required specificity of programming. You can't get both, at least not at the same time that we know of. So it's going to be an interesting battle.
Sounds good. Okay, we're going to go on to Cap, Steve Rogers. Just before Cap starts, I've decided as we were doing this that I just wanted to let it run open loop, and we've had a chance to really get into some good argument. Cap, do your thing as long as you want. Then I'm going to talk for about all of 30 seconds for my piece, because I want to save time to take as many questions as possible at the end. And maybe we overrun 4 o'clock by a few minutes. Okay? So it's important to me.
Doug, you can talk for 30 seconds in your life. I don't think that's going to happen, but
watch me. But please.
I got you. We'll go. So here's our big question, and it's, what are the principles for representations? And I want you to think consciousness. I want you to think qualia, and I'll sort of explain what I mean by that enable flexibility. So if you stick with me for maybe 5 or 7 minutes, I'm going to weave a story for you that uses the words of this question to give you the way we think about AI going forward, and specifically the role of consciousness. And so the first, what are the principles? In the 1700s, there was a French philosopher who, if I might paraphrase him, suggested that principles compensate for the lack of facts. And when you're talking about what's going to happen by 2040, or certainly if you're talking about consciousness, we have a lack of facts. So I feel pretty confident focusing only on principles at this point. So what are the principles for representation? So the representation words, I just want to clear up how we use that. Representations to us are how an agent structures its knowledge, as well as all the processes that agent uses to use that knowledge to create meaning. And then the meaning is what changed inside the agent. For example, the states, which causes it to have some behavior or take some action. So we're after that. And then you get to the Q word, the consciousness, the qualia word. So if you go to the next slide, to clean up qualia, to clean up consciousness, I need to back up because a lot of people sort of throw around these terms. So I want to talk to you about how we think of them. Over the years, there's lots of literature out there where people talk about type 1, type 2 thinking, cis 1, cis 2, subconscious, conscious. For the purpose of this discussion, think of your gut response as sort of a cis 1, or there on the right from an Evans and Stanovich or Danny Kahneman or Gary Klein, any of them, you can sort of see the characteristics of that sort of a representation. The idea is that you get quick meaning, and maybe not all the information that went into the creation of that meaning, not all the knowledge that was used to create that meaning is provided to you. Now, a lot of people, including myself, I admit I'm guilty, have suggested that current approaches, for example, in deep learning, provide us cis-1 sort of behaviors and capabilities. And to some degree, that's true, but I just have to point out And we had to replace the picture I had in the middle here because I didn't have it cleared. This is not the picture I want, but imagine a person like that patient who has what's called blind sight. So this person has no conscious access to the visual information, but yet you put them at the end of a cluttered hallway and they can dodge the objects, including ducking underneath. The point I'm trying to make to you is there's a lot of things that go on at the SIS1 level, which are quite complicated and far beyond our current capabilities. I mean, we have examples in the literature of showing an image, and it's been demonstrated that without consciousness being involved, you can tell whether the image is incongruent or not. So his grandma, of which I'm married to a grandma, is she pulling out of the oven a chessboard, since we were talking chess earlier, or is she pulling out a cookie sheet? She's pulling out a chessboard that's incongruent. So imagine the SIS1 sort of deep learning system. You could do it, but it's not trivial. There's lots of literature to suggest that maybe 90% of our decision making is SIS1. We could argue about that. But the point I'm trying to make to you is I don't want to relegate my current view of the representations that go on for the calculations that go on without consciousness as trivial. I need to put that to bed. If you go to the next slide, I want to sort of capture what I mean by consciousness, SIS2. So that cartoon in the middle is sort of the, Dennett illusory Cartesian theater. Okay, so the idea, the metaphor that you could use to think about what I mean by consciousness is you have this little person inside of your head, if you will, homunculus, which is seeing your sensory motor world model, and it has moods and emotions embedded in it. So there on the right, I give you a red patch. You see that patch, and what you see in your mind's eye is the qualia, Q-U-A-L-E, is the singular or qualia, which I used in the research question, that's evoked in your consciousness as a result of that stimulus. And if we change the hue, saturation, and brightness just slightly, you get a slightly different qualia, okay? So qualia are the atoms from which you create this sensory motor world model, which I'm going to call your conscious experience. And if Rockstar Doug plays me a tune using his musical talents, or even Tom, terrific, he has musical talents. Hopefully they're playing me a piece from Schubert, the best music ever created by a human. What I hear in my mind, in my mind's ear, if you will, is this conscious experience. There's something that is like for me to hear that or to see that. But yet those photons stopped at my retina, the vibration stopped at my eardrum, but the conscious creation is way up in the deep layers of my cortex. Or the taste of a Giovanni's pizza from downtown Fairborn, Ohio. That's created for me in my conscious experience. Or most importantly of all, there on the left is me holding my new granddaughter, Belle, okay? The emotions I experience when I hold her. We won't talk about what I experience when I'm interacting with my grandsons. That's not important. Or when Belle and I take our favorite companion, Napoleon, there on a walk, who you see in my background also, down to the beaver pond. We're overwhelmed with sensory motor information that's posted in this world model and allows me to create a representation, which I believe leads to the flexibility I have in a lot of the things I try to create. Or the overwhelming nature of when I, a couple of years ago, buried my father at Arlington with full military honors. All the emotions, all the moods, all the things I saw and sense and recall are created as part of this conscious representation, all right? And so we're going into this with the understanding, with sort of the positioning that consciousness is the key to that. It's if I'm going to ask now, back to my question, what are the principles of representations, qualia? If I'm going to start talking about the qualia now, what are those principles? If you go to the next slide, the principles, they have to answer not only the nego, what it is like for me to have a conscious experience, they got to explain the characteristics of my world model. But because I'm an AI guy, they got to explain why is it like the way it is? Because I'm going to assume why it is like that way, right? Why the experience, why the sensory world model is the way it is because it affords me some flexible cognitive behaviors. And so, we came up with this S3Q theory of consciousness. And so the first S is your sensory world model, all the concepts, all the qualia that are part of it are situated. They only have value with respect to how they're related to and how they can interact with other qualia. Okay, that red I showed you is not a number, it's not a wavelength, it's a concept which has value compared to the other concepts which could have been put in the world model at that location, for example, that other color. At that location, at that time, if I might use time in this sense, not in the Tom sense, but in the qualia sense. Time is a qualia also. It has a completely different representation as a qualia versus wall clock time. So the second S is the conscious experience is a simulation. There's a decoupling between reality and this representation, which we call consciousness. And there's lots of people who have concluded this. For example, I might reference Larry Barcelow down at Emory, who suggests to you that all your conscious experiences are the result of you cranking up these simulators, and that's how you bring to bear all the context of previous experiences to that particular phenomenology at that moment. And then the third S is structural coherence. And this is where I have to sort of try to associate with what Jan was saying. The world model, I don't believe represents that unconsciously experienced represents reality, but there has to be enough reality to allow me to interact with the world in a stable, consistent, and useful manner. So I struggle with the objective function I need to make a coherent enough narrative for this conscious experience. And so that's the third S. So I'm stable, I'm consistent and useful, and it's a simulation, which is the representations, the elements are the qualia, the cube. So the qualia are the result of this bottlenecking phenomena, which happens to have you create this simplified world model. I think what nature figured out was, don't try to represent reality. Try to create a simulation which is useful to you and stable and allows you to do those things that you need to do. So to me, consciousness is the essence of the question we have to answer. And the reason we have to answer that is, again, I believe that's our only shot. It's our only shot to get to moral, ethical, responsible AI that's flexible and robust. And so that's what we're focused on, is how to create that artificially conscious representations. Let me stop there and give Doug still a chance. Randy.
Quick comment. Some years ago, I looked back at some of the evidence about evolution and the human mind. And what I eventually wrote very briefly on the subject, one phrase was, given the way evolution works with constant reuse and add-ons and a complete lack of anything like what we would call design, the notion that the human mind would have simple and elegant set of fundamental laws, that's a little bit like saying, look, it's a 200,000-year-old legacy program. You expect structured programming in here? It's a mess. It's physiologically and anatomically a collection of dinguses and add-ons. And I'm quoting from somebody here that I don't remember at the moment. So I'm with you on the rest of this stuff, but I think if you insist on a simple and elegant set of fundamental laws, you have, to quote the old joke, physics envy, and you probably don't want to do that.
No, it's a great point. And the question will really come when as we instantiate these principles into practice. And so which of these principles survive? Which of them go by the wayside? Can you put them on in the David Chalmers sense? Can you put them on the front of a T-shirt? These principles, what these principles are, is a set of approximately 30, sets of examples of experiments that we've crossed over, and we bin them into these categories. So I use them as a way to do that binning. And I absolutely concur that I'm not convinced they're right. I do like the idea of there being some ability to do these simple principles, but I also buy off on your point that is, nature is a result of an ugly set of computations. But my fundamental thought there, Randy, is that about the time of the Cambrian explosion, nature figured out reality is not what it needs to survive. And so my suspicion is there are a lot of organisms out there which have conscious experience, and their representations probably follow a similar path, if not the same path. Over.
Jan, you look like you're thinking about a question.
Yeah, I think before we talk about before we can understand in concrete terms what qualia and consciousness and things like that mean, we had to have a model of the mind, regardless of whether it's artificial or natural. And before we have some decent idea about how this all fits together, those concepts, I think, are somewhat meaningless. So I tend to sort of not pay attention to them. I think before we get to the to human intelligence, like, you know, something I repeat often is that the best AI systems we have today have less common sense and knowledge of the world than a house cat. And I'd be perfectly happy if by the end of my career, which is not happening too far in the future, we would have a system, we'd be able to build systems that, or train systems that have the same level of common sense than a house cat. And that is way before we get to human intelligence. But I think the basic architecture is fairly similar. So, you know, we're talking about reasoning and planning. You know, cats do a little bit of reasoning and planning, not a huge amount, but they have a pretty good model of the world, certainly a very good model of intuitive physics, certainly of their dynamics, but also of, you know, behavior of things they chase. And some causal inference, you know, some cats can figure out how to open doors and, you know, open faucets and stuff like that. There's a lot to be learned from kind of simple animal learning. And we have, if we don't have the computation power yet, we'll soon have it. A cat has something like 800 million neurons. It's not that large. We're getting to the point where we can actually run neural nets that are roughly that size.
So let me say a couple things there. I'd be happy making a cockroach myself, but I honestly, I don't know why anybody would ever have a cat. Dogs are much better. But if you leave those to the side, let me just say, I'm going to give you an example of, and this is sort of a Randy and a Jan comment here, that is an example of where these principles are driving us. So earlier we talked about hierarchies, for example, and how difficult it is to figure out how to do them. I think one of the things these principles are pushing me towards is that that is not the right approach. That in fact, that if the fundamental unit of conscious cognition are situations, then all you're arguing about is a standard approach to processing with situations being your units. And there is no abstraction of situations, they're just situations. Some, to you and I, looking external, look like they cover more time or more space or whatever. But the point is, a lot of those issues architecturally get set to the side because of these sorts of principles. Now, it's yet to be determined, will they give us the robustness and flexibility? But that's sort of what we're after by taking this approach. Over.
Yeah, I mean, we certainly agree on the importance of hierarchy and abstraction. That's and I mean, I can relate to what you said earlier about the fact that you know, you develop the representations of the world that are useful to you. You don't necessarily, but this is to some extent what, you know, supervised learning does. It's very good at, you know, getting a system to learn representations that are useful for the task. But then the result of this is that the systems tend to be a little brittle when the task shifts. And so this idea that you should learn representations that are somewhat independent of the task so that it can be quickly adapted to any task is kind of the idea of self-supervised learning, and probably something that takes place in most animals, just for the purpose of quick adaptation to new situations.
Very good. Thanks, Cap. We're getting down to very little time left. Let me bring up the next foil. Then we say something rather important. Next one. I won't be more than 2 minutes. I want you to take this as an assignment that came out of our getting together today. Get a copy of Society of Mind, book by Marvin. The book is on the internet as a PDF. Marvin points out that you can read the book in any order of pages, and you really should try that. Yes, there are page numbers in chapters, but not really. And he's saying the brain is not a linear machine. Now, I've done this for all my students and friends. With this book, do not read it, just skim read it, then put it down. Wait at least 2 months and go back and skim read it again, and then put it down. And when you skim read it in any partial ordering that you like. But after about 6 months of letting it germinate, then you're ready to read what Minsky's really trying to say. And that's the third time you read it. You will encounter the K-line theory of memory. You will encounter the transframe mechanism to understand causality. You will encounter many wonderful ideas. They are representations of as many great students as he's had over the years. So this was a picture of Marvin taken on one of the glass walls at the Media Lab. And he was drawing out the fact that the brain is many, many, many different functional machines. You know, I often talk about his little quote, you can't learn anything well until you've learned it many different ways, which means you have many different representations, which means you have many different level bands. That's another fundamental idea in society of mind. Level bands allow you to work up and down levels of abstraction when thinking through something, whether consciously or unconsciously. So I would argue this is important to do. Next slide. So what are K-lines? They're wire-like structures. They actually sit at a certain level, as Marvin talked about it. They sit right above a lot of the work that Jan has done with his deep learning and with his earlier work with backpropagation and many others in the field. He does have a theory about levels, but again, you'll find that in the book. But it connects many different agencies of the brain, an agency of color, an agency of size. If you look below, he's got 4 agencies here: color, size, material, and shape. And the idea of a K-line is to connect those agencies that are associated with something that you feel good about. Oh, that's an emotion. I could go off on a tangent on what to do with that too. But these pictures are not silly pictures. They really are serious stuff. And I could fit them into Tom's work, Randy's work, Jan's work, Cap's work. You know, you have difference engines. So you may have different sets of K-lines activated because you have 7 plus or minus 2 temporal stores, temporary memory. And you can compare them and perhaps find something in A and you find something in G and say, wait a minute, let me put them together in a new way and have something in X. And on the right-hand side, I'll leave it to your opportunity of reading, you'll discover transframes, where you build up everything about a situation, you know, and you determine what's important. In this one example, you know, Marvin is talking about the origin is Boston, the destination is New York, and there's a whole bunch of different things that come to play of how you're going to travel from Boston to New York. I kid you not, I have used these ideas of Minsky in most of my work for at least 30 years, and they are powerful ideas. I would encourage everybody to go out and let go, and imagine what these things really can do in some problem space that you're working on. I'm going to stop there because I want to turn this over to my dear friend Scott, who's been collecting questions. And we'll go for a while until everybody says, okay, that's enough. Okay, that wasn't 2 minutes, but it's pretty damn close for me. Scott, I hand the baton to you.
All righty. We've got a bunch of good questions that come in from folks here. I guess one of the first ones that come up was the question about where does knowledge come from, and I know a bunch of folks have touched on that here today, the sources of knowledge and the where we've been born with it. It's programmed in. That there's some other systems been mentioned, embodied AI, physics informed learning, these kinds of things. I want to get the I guess the rest of the panel's thoughts on that question. Where does this knowledge come from? Where is it going to keep coming from? Kat made a strong statement that that machines are going to be generating knowledge quite a bit henceforth. So what do folks think about that?
Well, there's always the debate, the nature-nurture debate, right? Which, of course, is a big question for people who are, in favor of sort of machine learning-based, data-driven approaches versus kind of exploiting human knowledge for, getting machines to reason and things like that. I think there are several ways in which knowledge about or prior knowledge can be embedded into an AI system, including one that learns. It can be embedded into the architecture, which of course is what most practitioners in deep learning today, basically what they do is that they design new architectures for new problems, new network architectures that hopefully have the right inductive bias or better inductive bias than others. Then there are different learning paradigms and objective functions. But one way nature drives us towards learning certain types of behavior is by hardwiring an objective or a collection of objectives. I can take an example. Certain primate species like humans, baboons, chimpanzees, etc., are driven to seek the company of other members of their species because we are social animals. We have a hard time surviving by ourselves. We need the help of others. And with this comes also hardwired behaviors for social interaction and social relationships, like relationships of submission and dominance and hierarchy and social hierarchies and stuff like that. Orangutans, on the other hand, are not social animals. They largely live solitary lives, and they don't have any of those kind of hardwired objectives of seeking the company of other members of the species. In fact, they avoid each other, at least in most situations, and they're territorial. And so a lot of what we normally associate with intelligence, things like social interaction, as humans, we associate a lot of what we think is intelligent behavior with language, with communication, with social learning, culture, etc. But there are animals that are very intelligent and they're not cultural at all. They are solitary. So orangutans are an example. I mean, there is a mother-child relationship. Another example is octopus. They don't even know their parents. Their parents die when, before they're born. So, and they only live a couple of years, but they're pretty smart. Like, how does that work? That's a big mystery.
Okay, Scott, do you have a question in there from JC Leday by chance?
Unless he's listed as an anonymous asker.
Okay, no, you're right. I'll get him. I'll do it at the end.
I've got an answer. I've got an answer for something Dr. Roach asked at the very beginning, or at least a shot at an answer. May I?
Yes, definitely. Please.
You were asking about hype and being careful about managing the hype. Is that true?
That's correct. You bet,
Okay.
Tom.
One of the things that I think, if we had a way to do it, would have an enormous impact is educating journalists, because I almost inevitably lose a molar every time I read one of these stories in the paper about how, the next great thing has arrived. I start grinding my teeth and it makes me crazy. My own favorite example was a report back probably like 5 years ago now, where it said a Google computer learned to recognize cats learned to recognize cats by watching YouTube videos. Okay. Now, in fact, the work they were reporting on was a very interesting piece of work in unsupervised learning. Technically, it was actually quite interesting. The story that got published was how the computer just watched a whole bunch of videos and it learned to recognize a cat. In fact, it learned to recognize a frontal view of a cat face. If you got a side view, it wouldn't see it. If you saw a whole cat from the side, it didn't recognize it. It had no idea what a cat was. It had no idea about cats and milks and kittens. The whole story was so bad. And it really struck me because this is Wired, who ought to know better. And there was, in fact, a very interesting technical issue underneath all this, but they turned it into almost complete nonsense. So how do we educate the press to do a better job of explaining what's going on in the field? I think that's one of our leverage points.
Yeah, Randall, and I apologize. I said Tom, and I
noticed.
I'm wondering if he was asking the question, but thank you for taking that on. Let me tell you what I see as the negative impact of hype from the funder point of view of science. When we go out here with these new things, QIS is going to save the world, right? Directed energy is going to save the world. All these different things. Yes, they're really important areas of research in science and engineering that we must get at, because all the evidence points to our potentiality there. But when those things are oversold to funders, right, they get sort of numb to it all after a while, and they begin not to trust, right? Here comes that trust and influence part again, the outcomes when it's overpromised. And they begin to withhold funding and they begin to withhold resources, which in my opinion is very critical to communities to actually make those breakthroughs that are going to happen in the future. And this, in part, from my part of it, is why it's so important to manage realistic expectations for people across the board at all levels of strata and government and academia, so that we have a really good, honest dialogue about what is capable at the moment and what is not, and what is potential and what might be, right, realistic in the future, without overselling it, without overhyping it. And I think this is a critical point. And this is a technology that we're all looking at to alleviate so many things, right, in the future. So much has been written. I agree with you, Randall. The press is probably the worst, because I don't think we do a good enough job speaking truth to a lot of different entities going forward. So thank you for taking that on. Over.
I think the press has made a lot of progress since, in the last 10 years or so, since that paper that you mentioned. It used to be that every single article published on AI on the web had a banner with a Terminator on it. And, that subsided, which I'm really happy about. So I think there's a lot more knowledge, but then with this comes kind of more fear to some extent, more like, or more criticisms, and perhaps it's a good thing in many ways. So I think there's progress, but certainly talking to the public and trying to explain what AI is all about is really important.
The other problem that we wind up in a feedback loop, Dr. Roche, because as the funders become less trusting, the applicants think they have to ramp up their claims in order to stand out and attract attention and get funded. So we need some sort of arms limitation agreement here.
I think to all of you on the panel, I think we all recognize that artificial intelligence If you recall, I was at AFOSR over 30 years ago in the mid-90s. I was a young captain managing a program called Sensory Systems. There was another colleague of mine by the name of Dr. John Tangney, who funded neural networks, specifically looking at now what has evolved into AI. And of course, we've gone away from those algorithms because of limitations, and we've learned a lot, and we've moved into a whole new realm of thinking and understanding. Certainly, and his name comes out all the time because of the Minsky background about how we learn K-line theory and how critical that has been in influencing a lot of what we do going forward. However, right, I don't want to see AI not continue to be one of the areas that we focus on. I want to make sure that we keep going because, again, I don't think the critical breakthrough comes tomorrow, next year. I think it comes in 10, 20, 30, 40-year increments of being very dedicated to study and academic endeavor, right? And those are long-term kinds of commitments I think we need to make to be able to realize the technologies that are going to fuel an economy, right? That are going to protect young men and women in our militaries, keep them safe, bring them home to their families, and all those things that we want to have happen. We have to stay the course. Over.
For everybody who's here and others who aren't, many of the questions are fantastic. We'll try and do as many as we can before we finally call it a day. I found out that we can go on, so we can answer a few more questions. And then offline, I'll try and get back to the list of questions from everybody in the weeks ahead. So don't fear that if we don't get to you today, we will get to you. Scott, I'll turn it back to you, please.
And to see if we had a good follow on to the question there. I think there was just a detailed question maybe for the panel as a follow on to those comments is can you how can you tease out some of these breakthroughs or try to find some of the engaging work that's being done that's not Epsilonian's style work, if you forgive the colloquialism there, in all of the things that are being published and all of the work that's being touted from all over the place. If there's some tips or tricks or the ways that you think about those kinds of things.
That is the one question that's the hardest one to answer. I think the main job of people who are spending full careers doing research in AI, that's 50% of what we're doing. We're trying to understand which of these small pieces of progress that are reported in different papers have implications that make them very important to follow up, and which of them don't rise to that level. So I don't have an answer to the question, but I think that's because it's a full-time job to do it.
Cap?
The thing that makes that so difficult is as a group, we as a community have fallen in love with very specific methods. And so we have that leaderboard mentality, and we try to ooze forward because you're temporarily on top of the leaderboard. So what my guys will tell you, like Scott will tell you, is I tell them to think deeply. Your challenge is to do less, but do deeply and know why. And so finding those articles which seem to not focus on performance, but focus on ideas. And I'm reminded when I first started down this path of consciousness, I had the privilege of talking to John Searle. And what John told me was, because I wanted to catch up, I wanted to know what should I read to understand what the current thoughts are on consciousness. And his comment to me was, there's never been anything written worth reading about consciousness. And so his point was, you start with a blank sheet of paper and you capture your ideas, and then you try to pursue those things that are making you think deeply about what you thought was true. And if you follow those trails versus trying to follow all trails, I have found that to be far more productive. Over.
Okay, Scott, give us some more.
There were some good follow-on questions to points that y'all had made along the way, and one of the questions I think was framed to Tom when you just after you spoke was about the interaction of agents, and Kat made some comments about that, but I think Jan and Randy, y'all were both mentioned in some of the questions there as to get y'all's perspective on the interaction of those agents. I know we had some discussion here just now about where knowledge comes from and social thinking and these kinds of things, but I think it was really framed more of where are the agents that we're building, the tools that we're building, and how they can interact with one another, as well as with users to potentially sharpen one another or adapt to one another.
Can I jump in first? For those who have seen me talk, I make a big to-do about many different engines to learn. You have to learn something many different ways. And maybe in the brain, there are 40,000 different little parts, engines. That's great. But the real trick to my talk is once you buy that quote from Marvin, then the question is integration. How do we integrate them, and not in a hierarchical way, but in a very fluid heterarchical way, as Marvin suggests? I think that's one of the fundamental questions that we need to address head on going forward. Integration as fluid. I'll stop.
This question reminds me of a book called Sapiens, which I recommend to everybody, by a guy named Yuval Harari. But one of the main points of that book is that human progress didn't come about at the rapid rate that it has over the centuries due to us individuals getting smarter, because evolution couldn't arrange that to happen so quickly. Instead, it came about because we became more social and arranged better organizations for sharing knowledge with one another. I think it's a very fundamental point, and so it also points toward probably the importance of AI doing the same.
Yeah, coming back to what you did in Now, you had an interesting architecture. You had 3 really phenomenal machines. But what if 3 became 300? How do you integrate them? And how do you use, Marvin comes up with words that forces us out of the box. So he introduces the idea of level bands. And again, you have to go back and read Society Mind to really understand Marvin's thinking. So how do we dynamically flip back and forth, up and down, left and right, between all these different engines, which are all active under different settings? We see a red fire truck, but in a second state of mind, in parallel to that, we see a green ambulance. From the 2 of them, we could easily also start to talk about emergency vehicles. We have to have this ability to bridge out dynamically at different levels all at once, and have these dynamic structures that light up like a Christmas tree. I'll stop there. I guess we will go for another question or 2 and then call it a day.
Well, I was gonna follow on. I think there was a couple of questions or several questions that I think you led into very well about scaling, about how to not necessarily not necessarily the integration of these heterogeneous systems, potentially heterogeneous systems. But how do you scale even the like systems that we're constructing? So we think about for example, solving a one-off problem or producing a tool that's exceptionally powerful at a particular task, and then adapting that to either adapting that to in a transfer learning kind of sense is a lot of terms that have come up, or generalizing that capability. Is that a viable way to proceed, or what do y'all think about that? I know I think Jan's probably got some strong opinions about about such things.
Maybe getting come on, Cap.
I'll just, the way we've been pushing on that guy is this idea, and it's not unlike Society of Minds, is the idea of having these capabilities be interoperable, but without standards. So the idea of interacting to be able to exploit knowledge from each other, be composable in the sense that they can combine together to do things that neither could do on their own. That's building a new vocabulary of capabilities. And then each individually being adaptable in terms of their representations. And so with those three technical challenges, that's how we see this scaling. It isn't, I don't think it's magic. Those are very tough challenges, but I think that's a very engineering approach to the way we're trying to increase our capabilities over.
Yes, Randy? For some reason, the system defaulted to you making a comment.
Who's you?
As in Randy.
Oh, no, I've made my comments for the moment.
Okay, sorry. All right, Scott, give us one more and we'll call it a day. Oh, wait, real quick. I want to thank Molly and her team. I want to thank also Sherry and her hard work. I also want to thank a few other people behind the scenes. Benji Mariama, Kathy Griffith, Lisa Versky, Scott Irwin. I think I got them all. JC Leday. They were all wonderful colleagues who helped make this come together. I thank you all.
And I'd like to thank Doug Rieken for conceiving of this,
Yes.
working hard to make it happen, and having it turn out to be a great day.
Well,
Yeah.
don't forget, this is just the first of many. We have we're a team, the 5 of us, 6 of us, because we're all part of this portfolio. But we have others in the portfolio with interesting ideas we'll talk about in January. Okay, give us a good question to close with.
So there was an interesting question, kind of dissimilar from a bunch of them, but it got a couple of hits. There was we've talked a lot here today about how we've learned from the way people think, and to guide some of the systems that we build, and some of the to hopefully incorporate some of that information into some of the things that we build and learn in similar ways. But are there things that we've learned along this research and development process to help improve ourselves? Are there it's kind of flipping the question on its head.
Yeah, I can offer one brief comment on that. It's something I pointed to in my presentation. This seemingly trivial question, why are experts experts, is, I think, quite revealing and is quite a democratizing, and the answer is quite democratizing, because it says you aren't born smart, you aren't born thinking faster than someone else. You're good because you learn a lot, you know a lot. And this has been established numerous times. World champion chess players have played for some ridiculous number of hours and have learned a very large number of positions. Physicians learn an enormous amount about anatomy and physiology. the important point is you can do it. If you learn it, you'll be good at it. It isn't something you're born with and something you have to have implanted. You can do it.
Yeah, there's, I mean, certainly some of the systems that we have at the moment are better than humans in very narrow domains, right? I mean, we have translation systems that can translate more or less well. You know, they're not perfect, but pretty well. 200 languages into 200 languages, right? I mean, any pair, that's pretty amazing. No human can do that. We have systems that can, you know, identify the species of an insect or plant just, you know, from a picture. And, you know, a few human experts can do this, but, you know, machines can do this now, and or birds or whatever. And if we have learned something over the last 10 years or so, is that humans are much worse than we thought at games like chess and Go. We totally suck at chess and Go. Machines are much, much better than we are. You know, before AlphaGo and similar attempts, the best Go players in the world thought they were, you know, only a couple handicap stones away from God, right? From the ideal Go player. And what AlphaGo and others have demonstrated is that, no, humans really suck. I mean, we are like 9 stones behind or something. So we're really bad at this, and machines are much, much better than we are. And so, you know, as AI progresses towards being more adaptive, learning more how the world works, you know, all the things that we talked about during this exchange over the next 20 years, perhaps, it's very likely that, you know, sometimes in the future, maybe not in the next 20 years, machines will become smarter than humans at all the tasks that humans are good at. That event, in my mind, makes no doubt. It's just a question of time. And some people may fear this, but I don't think it is to be feared. I think it is to be anxiously awaited.
Here.
I'm reminded
Tom.
I'm sorry. I was just going to chime in real quick.
Yeah, please, go ahead.
I'm reminded of a quote from Amos Tversky, who said, when asked about artificial intelligence, he said he studies natural stupidity. And he wasn't, you know, by any meaning suggesting humans aren't smart. His point was, is there's a lot of things, as John just pointed out, that we just don't do that well. And having spent a decade out in the commercial world building an AI to help detect breast cancer, you know, I found there are lots of these pockets where it's relatively straightforward why humans are not very good at it. You know, in a radiologist case, they don't get immediate feedback, so they can't get Randy's expertise. You know, they do their best and they do good, but with a machine, they can do much better. And so there's lots of these pockets, as Jan points out, where AI will help people live better lives. And that's got to be our focus. Over.
Right on. Tom.
I second that. I was just doing a thumbs up on that one. Well said, Cap.
Any closing thought?
We're at
Thomas.
We're at some of the earliest phases of an incredible adventure. We will look back on these times with, I think, nostalgia and surprise at our ignorance. But that's okay. It just means we've got a lot to learn.
Doug is ahead of us. He's already nostalgic of Marvin, so, you know.
I was going to close with that thought. This has been a wonderful afternoon. I am very grateful to have such wonderful friends to think with, because we're thinkers. I want to thank everybody, you know, Cap, Tom, Randy, Jan, Scott. And let's continue to see if we can see where Marvin has been going, because he's still pushing the envelope. You know, let's follow the envelope of these great opportunities to think about things to get us out there and beyond. I want to thank everybody so much.
Thank you, Doug.
Thank
Have
you.
a great day.
Yeah.
Yes, everyone.